Okay, so it's a great pleasure to introduce Omer Bobrowski, who's from QMUL right here in London. Omer's Professor of Mathematical Data Science at QMUL, and his interests are in stochastic topology, and he's going to talk to us today about universal distribution for the topology of random geometric complexes. Thanks, Omer.
Thank you. Yeah, thank you for the organizers for inviting me here. I should start by saying that I think this talk is a little bit of outlier in this workshop. First of all, my focus is mainly on probability theory, which is, I think, a little bit different. And also, the motivation is more from the perspective of spatial statistics rather than networks or dynamical systems. But I try to choose a topic that I think is sort of presents an interesting mathematical phenomenon that can also be potentially useful. So I hope I'll be able to convince you in that. And if you have any questions along the way, please stop me. Yeah, and this is John Falk with Primor Scraba, also from Queen Mary. So I'll start with introduction. Maybe some of the parts are already known, but just to cover the basis. So the world of what this kind of problem is mostly related to is topological data analysis, which was mentioned several times already. But sort of to give a motivation, I like this toy example where you suppose that you look at letters and you try to distinguish just between the letters A, B, and C. And toy example, a simple task. And the letters may come in various shapes and forms and angles and styles and so on. But when you count the number of loops that you see in each picture, then the letter A always has one loop, the letter B has two loops, the letter C has none. So just this simple descriptor, which is, you can think of it as a topological descriptor, gives you an immediate answer, which is quite simple. And that's the idea behind topological data analysis. Topology gives you, for the most part, global and qualitative properties of the shapes that have all these nice properties. They give you a compact representation. It's coordinate free, it's robust to various continuous deformations. And from the point of view of applications, since we're mostly looking at algebraic topology, it means that these properties can be encoded as solutions to linear equations, which you can write algorithms to solve. So everything can be done in software. And it's been applied in many, many different areas of application. This is just a small subset. This is a picture taken from a cosmology study, biological imaging, incorporating topology into loss functions for neural networks, and there are many, many, many other examples. The place where hypergraphs enter this talk is as simplicial complexes, more specifically. And the idea of here is to use simplicial complexes in order to convert data into shape. So whenever we convert data, we want to build some shape in order to study the topology. And throughout the talk, the setup will be that we have some point cloud, a collection of points in space, and we want to convert them into a simplicial complex. And the two main ways that have been used in TDA, in topological data analysis, and they both start by placing a ball around each of the points. One construction is called the check complex, where what we do is we place simplexes according to intersections of the balls. So two balls intersecting will produce an edge. Whenever we have three balls intersecting, that would be a triangle. When we have four balls intersecting like here, that would be a tetrahedron and so on. So we have a simplicial complex. And another construction, which is quite similar but has some differences, is the Vietoris-Rips complex, where instead of looking for k-wise intersections, we just look for pairwise. So whenever we have all the edges in a simplex, we immediately put the corresponding simplex, which it's also called a clique complex or flag complex. And in this picture, you can see the difference between the two. So here we have all the edges, so we also include the triangles, but here the three balls do not have a common intersection, so these two triangles are left empty. And so they are very similar. One can be used to approximate the other, but there are mathematical differences and also computational differences when you try to compute one versus the other. But I will refer to both of them in this talk. The type of topology that is related to this talk, and mostly in TDA, is homology, which I think was mentioned in this workshop already. Basically, we have for every space, we have a sequence of groups of vector spaces representing different kind of features. H0 represents connected components. H1 corresponds to holes, or what we call one cycles. Then you have H2, which you can think of as bubbles or air pockets. And in general, we have the k-dimensional homology representing k-dimensional cycles. The Benny numbers are the dimensions, so they count how many independent k cycles we observe. And these are a few examples. So for example, the circle has one connected component and one hole or one cycle. The sphere has a two-dimensional cycle, the entire air pocket. And then the torus, the last one, has one component. There are two independent loops or one-dimensional cycles, the red and the blue. And then the entire air flowing inside the torus you can think of as a two-dimensional cycle. So this is the kind of topological properties we're interested in. And I mainly work with random geometric complexes. So the whole story about those simplicial complexes built geometric on point clouds and look into homology in the case where the points are random. So the picture is something like that. You deploy some points in random in space. It can be Euclidean space, it can be something else. And then you build one of these constructions, placing the edges, the triangles, and so on. And you can look at these shapes and ask probabilistic questions about the topology, specifically about the homology. So the kind of questions people are trying to look at is, so the one I'm mostly interested in is to look at sort of phenomena that are well known for random graphs. For example, questions related to connectivity or percolation in random graphs. You can use a homology to have higher dimensional version of those with a lot of interesting both challenges and insights about what's going on. You can also look at quantitative statements like central limit theorems. For example, if you look at the Benny numbers, the number of holes, then it's a random number, and then you can prove that it converges to the normal distribution. So that's another aspect. There's some work on extreme value theory. What happens if you have distributions with unbounded support and you have all these outliers far away? What is the topology of the outliers? There's also a recent study on large deviation, sort of very rare event that shouldn't happen, but when they happen, exactly what can you say about them? So these are all sort of kind of probabilistic questions related to the topology of this structure. Important point about most of the results in this area, which is related to this talk, is that whenever you prove something, the results, the methods, everything is sort of highly depend on the underlying distribution. So there is distribution to how the points are deployed in space. For example, this is, I think, uniform distribution, but it can be normal distribution. You can sample from Euclidean space, you can sample from a manifold, you can sample from a fractal. So the results heavily depend on how you generate the points, which sort of makes sense. Now, moving back a little bit to topological data analysis, the sort of the challenge, the main question that is related to what I want to talk about next is called topological inference. One of the sort of very first questions people try to ask in topological data analysis. Suppose that you get a point cloud. When you look at it, obviously there's some shape, there's some topology here. It looks like it was sampled from a circle or an annulus. And the question is how you deduce that. And then, okay, you can build, you can cover it with balls, you can build the check or the Rips complex that I presented before, and that sort of gives you a hint that there's a one hole here, one component, which is what you would imagine. The main problem is that there is a parameter here, and the choice of parameter, different choices will give you different answers. So in this case, the parameter is the radius of the balls that I used, either to draw the picture or to construct the geometric complex. And you see different radii, it's increasing in this way. Give you different answer. There's a hole here, there's a hole here, which probably are not very interesting, not what you imagine as the shape of the data. And in the last picture, the radius is so large you don't see anything. And the question is how to make this inference about the topology with this sensitivity to the radius. And that's one of the main ideas or the main motivations to develop what is called persistent homology, where instead of trying to choose the correct picture, we just look at the entire sequence. So persistent homology looks at, in this example, we take all possible radii. We start with 0, we increase it until everything is covered. And then we sort of look at the multi-scale version of homology. We try to look at what happens to homology throughout this process, throughout this filtration. And then it's often summarized by a barcode. The barcode represents the feature or the holes that you observed in the data, along with the time at which each of them appeared and disappeared. So in this example, there's this small purple hole that appeared at R2, but got filled in and disappeared. It will be represented with a small bar here. There's another cycle that appeared at R4, survived a little bit longer, but then again got filled in. So that's another bar in the barcode. And so on. And finally, there's one bar that is substantially longer, the green one that appears later, but also died much later. And that's what we get. Another representation, which will be more useful for us in this talk, is called the persistence diagram, where instead of bars, you represent each bar with 2 coordinates, the birth and death, and then you get 4 points corresponding with the colors. And the intuition is that this diagram should give you some indication into what is interesting in the persistent homology and what is not, what cycles are important and what cycles you should ignore. So if you look at this picture, right, one bar stands out as being very long, one point here stands out as being very far from the diagonal. So the difference between death and birth is very large. And that's what we might consider as the signal, the important and interesting information in the data compared to everything else, which we would think of as noise. Okay, the noise is an artifact of the random sampling, the fact that it's finite and so on. This is an intuition. It's not a statistical statement, and part of what I'm doing in my research is to try to quantify these kind of statements. Just to add to that, persistent homology also, in addition to providing this picture, there are also ways to compare between persistent diagrams. So there are different metrics that you can use, and in this example, in this talk, we'll be thinking about increasing radii and building those simplicial complexes, but you can work with any filtrations. Okay, so getting closer to the topic of this talk, what I want to talk about today is random persistent diagrams. Namely, we start with some sampling space, call it S. We have a probability measure on this space, which gives us a way to generate points, and then we generate a point cloud. The point cloud is random. There's a star here. I don't want to be too specific at this point what random exactly means. So that's the picture that we have. And then we can use our favorite construction out of the check complex that I showed before, the Vietoris Rips, or maybe there's another option. So we have some structure. This structure gives us a persistent diagram, so we can look at all the cycles. Each of them appeared and disappeared at different times. So we have a collection. So K here is the dimension of homology, whether it's 1 cycle or 2 cycles, bubbles, and so on. And we have lists of birth and death, these pairs. Now this list is random. This collection of points here in the plane is a random collection of points. And one of the main questions people working in stochastic topology with respect to TDA have tried to answer is, okay, suppose that I know something about how the points were generated, the sample. What can we say about the distribution of the points here? So there's some transformation taking you from these points to these points. What can we say about that? And that's a very difficult question to answer, but in this talk and most of the analysis that you have, the focus, so I mentioned earlier, you can sort of separate this diagram between the signal, the important feature, the hole that you see here, and the noise, which is everything else. The probabilistic analysis mostly focuses on the noise part for 2 main reasons. One is that the signal cycles, right, in this example, you only have 1 signal. There's only 1 hole that you're going to see. But depending on the number of points you have, you might have a lot of noise. The signal is very large, the noise is very small. It's quite different in terms of what it represents, the distribution of it. It's not the same object that we can sort of put together. So we separate the study, and the noise cycles are more random in some sense. And for the purpose of doing statistics, we want to try to say as much as we can about the distribution of the noise, which will allow us later to do a hypothesis testing, for example, and have some null distribution for the noise that will allow us to distinguish that from the signal. So the analysis that I'm going to talk about today only refers to the noisy part of the diagram. Okay, and that brings me to the main topic that I want to talk about, which is, so I'm looking at this random persistent diagrams, and I want to look at universality in their distribution. And just before making it a bit more formal, what do I mean by universality here? So in my mind, universality here is in the same flavor as the central limit theorem. So the central limit theorem, quite well known, you take a sequence of random variables, you sum them up, you normalize them properly, and it's quite well known, but it's a little bit of a magic that no matter how you sample those points, how you generate those values, it always converges to the normal distribution. So in that sense, the normal distribution is universal. It describes many different types of data, and the idea is that you don't need to assume much on the data. As long as the sample size is large enough, you can assume it's normal and move on from there. Another interesting example is coming from matrix theory, where there's something called Wigner's semicircle theorem. So there you look at random n by n symmetric matrices, and you look at the eigenvalues of the matrix. So for a very large class of such matrices, doesn't really matter how you generate the values in the matrix. The distribution of the eigenvalues follows the semicircle law, which also it's a little bit of a magic. Okay, and the idea is that those results, this behavior doesn't depend on how you generated the values. For example, the normal distribution, your variables can be 0, 1, they can be exponential random variables, they can be bounded, unbounded, it can be discrete, continuous. It doesn't really matter, it always converges to the same thing. The samples can be independent, but they don't have to be. So it's quite a powerful and interesting phenomenon. And we're sort of trying to find something like that in persistent diagrams. Again, if there are any questions or comments, please stop me. Okay, so our journey sort of starts here with this simulation. So just a very simple test. So we took here two-dimensional point clouds in different settings. So this is uniform distribution on a box. Here we sampled points on the Klein bottle, and this is two-dimensional normal distribution. So 3 different ways to sample 3 different spaces. For each of them, we're looking at the k = 1. So these are 1 cycles, the loops. And we plot the persistent diagrams here using the Check complex. And you see the diagrams look quite different. The distribution of the points in the diagram is quite different. Here we estimated the density rotated in 45 degrees, and the densities look quite different. There's nothing like shows up like a uniform, normal distribution or something that is the same between those pictures. So again, just with these 3 examples, it doesn't seem like we can say this is the same distribution in any sense. Okay, so it's not a great starting point, but what we're going to do in order to find something universal is to change the question a little bit. So instead of looking at this collection of 2-dimensional points and ask about the 2-dimensional distribution, we're going to sort of project them down on 1 dimension. And the projection is done via what we call the multiplicative persistence values. So instead of taking the 2 coordinates, we just divide one by the other, and we call it pi. So we take the ratio of the death divided by birth, which gives us some sense of how big the cycle is. I'll tell you in a second why we think it's a useful quantity to look at, but this is the values that we look. So now we have a collection of numbers rather than points. And what we want to look at is what is the distribution of these numbers. Okay, so you have a diagram, you have a point cloud, you produce a diagram, you take this diagram, you have now a list of numbers corresponds to these ratios, and what can we say about that? So before I tell you what we found, just try to convince you that this is an interesting functional to look at. So suppose that this is your point cloud in 2 dimensions, and what you can see in your eyes is that there are 3 main loops or cycles. One is this almost 8 here, there's another one here, and there's here you can also create this loop. Now intuitively, there are 2 issues here. One is that in terms of if you want to try to say which phenomenon is more significant, is more important for you to detect and analyze, then this almost figure 8 here is exactly the same as this one, just different scale. So if this one is significant, so should this one be. And another thing is that this cycle here is mainly generated by just 2 outliers that just happen to be there. Okay, so it doesn't seem to be like a robust, very interesting phenomenon. But if you look at the diagram that corresponds to those, then the point that most stand out is actually the blue one because it's just physically big. And here, those two cycles have sort of different ranking. If you just consider the distance to the diagonal. So these are just the numbers. The difference between death and birth is bigger here than here, and it's the largest here. So just looking at the length of the lifetime of a cycle is not necessarily a good prediction to how important it is. If you take the ratio, then both of these issues are sort of fixed. So if you take the ratio, because this is the same structure as this, just at different scales, then it disappears. So you have the same ratio here as here, so it tells you it's sort of have the same significance, and also this cycle now becomes the smallest one of the three. So it tells you that maybe it's less important than the others. So it's both scale invariant, which is important, and it's robust to outliers. So it's an interesting and useful quantity to look at in the context of persistent diagrams, and it's just not just something that we made up. Okay, so I'm going back to the picture that I showed you before. Okay, so we have three different settings, two-dimensional point clouds, different diagrams, different distributions. Now, what I'm plotting here instead is the one-dimensional CDF function for those ratios. Okay, so I'm taking every point here, divided that by birth, and then plot to the distribution. And you see those three pictures, which now look very, very similar. And when we actually plot them one on top of the other, they're identical. Okay. And this, when we first observed that, that was very, very surprising, because we're basically sampling here. Everything is two-dimensional, but we have spaces with different geometry, the box, Klein bundle. We have different topology, and we also have different distribution, normal distribution, uniform distribution. The diagrams look vastly different, but somehow these ratios have exactly the same distribution. And as I mentioned earlier, all the other results in this area, the probabilistic results actually do depend on the underlying distribution. Here somehow it doesn't. And so the first thing we did was to spend actually several years to try to explore this phenomenon just experimentally, try to look at many, many settings and see what exactly is happening. So I'll show you most of what we found out. So this is the same picture we had before, maybe with a few more examples. So there are several distributions here where we take in two-dimensional point clouds and one-dimensional homology, and they all coincide. If we change the dimensionality of the data, so now it's three-dimensional point clouds, so still all the examples we choose coincide, but along a different distribution. We go up in dimension 4, so a different distribution. We can also change the features that we look in. Instead of one cycle's loops, we can look at two cycles, which are these bubbles. And then again, everything coincides, but it's a different distribution. So the first conclusion is that at least if you fix the dimensionality, so you fix the dimension of the point cloud, you fix the dimension of the features that you look at, then there is a universal distribution. So it's just one thing that describes your data regardless of how it was sampled. Now, this was for the check complex. I told you there are two different structures we can study. So for the RIPS, it looks quite similar. There's a little bit of discrepancy here, but we'll resolve it later. But it still seems like they're grouped together according to dimension, and it's quite the same. And there is also a difference between those distributions. So it depends on what construction you're using. And the bottom line from these simulations, at least, is that as long as you fix the dimension and you fix the construction you're using, you end up with this universal distribution. So this is what we call a weak universality, because there's going to be a strong statement later. And this is something we recently finished proving. And the statement is roughly like that. So you fix the dimensions, you fix the structure that you're using, and then you can choose almost any. It's quite large classes of distribution. So choose a space that is d-dimensional, choose a probability distribution. The points have to be independent and identically distributed, but otherwise you're free to choose your distribution. Take n points from this distribution, look at the diagram, and then what we do is we compute an empirical counting measure. So we just look at these values, we place a delta function on top of each value, and we look at this measure. And the statement that we prove is that you normalize it by the number of points, you take the limit, then the limit depends on d, k, and t, these parameters, but it doesn't depend on the sampling space, it doesn't depend on the sampling probability. Yeah, this is a result that we finished proving recently. Yeah. How much time is left?
I would say till 1:45.
Oh, okay, that's a lot. Okay, so just in one slide, just to give you an idea of where this phenomenon is coming from, or okay, it should be okay. Okay, so there are two key things that are sort of related to this pipeline. So we have a point cloud. We generate the diagram. If we want to look at the distribution of those ratios, a proxy for that would be just to count how many points we have with some fixed ratio. So we look at this diagram, we want to count how many points we have such that the ratio is bounded by alpha. That will give us, that's an indicator for the distribution, which basically means you draw a slope here, y equals alpha x, and you count how many points you have here. And you have to do that for every alpha, that will give you the distribution. But the point is that if we fix alpha, and now we scale the point, so we shrink the point cloud here, everything will shrink accordingly here, but the number of points that we count doesn't change. Okay, and the same if we expand the point cloud, everything expands accordingly, but if we just look at this cone, nothing moves in or out. And that's the first observation that enables the proof, which is that this functional, if we count how many points with a bounded ratio, it's scale invariant. It doesn't care about the scaling of the points. And this is sort of a topological or geometric topological statement. The probabilistic statement, which is most important here, is sort of near additivity. So if you have 2 point clouds, you put them one next to the other, you can count how many cycles you have here, you can count how many you have here, or you can count in the entire point cloud. And the point is that this almost breaks up additively, so you can just add this and that. And these two facts sort of enables us to produce this universality result. It's a long process to get from here to the proof, but these are the main ideas. And in fact, what we prove is a more general statement. So you can look at functionals of points that not necessarily persistent diagram, but as long as they have these properties, you can show that they have this universal limit. So persistent diagram just happened to be one example. Okay, so this is the story of weak universality, which, as I said, is mostly proven by now. And along our experiments, somehow we ran into what we call strong universality, which is much more surprising, at least to us. And at this point, it's only at the level of conjecture. And it starts with a little bit of a weird transformation that we do. So just to remind you, we start with a random point cloud. We look at the persistent diagram as a collection of pairs. We compute those ratios. So we have a list of numbers, bless you. And now instead of looking at the distribution of these values, we apply this weird transformation. We take the log of pi. There's some constant here, there's some constant there, and then we have these new values Li. So we have a collection of new values that were just this weird normalization or transformation. A and B is something that we know, again, from the experiments, what they should be. But if you do that, then, so these are the pictures we had before. We had several curves here, depending on the dimension of the data and the dimension of homology, and several curves here, and it's different for the check and the rips. If you apply this normalization, then all the curves that you have here now seem to align along the same distribution. Same thing happened for the rips. And also this discrepancy I was telling you before sort of vanished now, so you don't see them. And moreover, if you put the check and the rips one on top of the other, they're exactly the same. So in this setting, if you apply this weird normalization, then you end up with, no matter how you choose the data, no matter what the dimensionality is, what kind of homology you're looking at, doesn't matter what construction you're using, there's just one distribution that describes the sizes of the cycle in this multiplicative way. And there is nothing in the literature related to that ever shown up or suggested that this should happen. At least mathematically, it's very surprising. And it's also distribution. That's the next thing. Thank you. It's an invited question. So yeah, if you already asked, so then two follow-up questions for this experiment is this a distribution we can identify? And the other thing is, all the settings I showed you here and the proofs before were focused on IID, so the points are independent. Does it still hold if there's no independence, or does it hold in real data? So we, again, experimentally, after checking every possible distribution, we found this one, the left-skewed Gumbel distribution. So this is the density. And somehow by miracle, they fit quite well. Okay, so this is the dashed line is the Gumbel distribution, and here there are like 20 curves from different samplings, and they all align nicely. This is the CDF, the PDF, and this is the QQ plot where you want things to be aligned nicely along the diagonal. So it seems, again, this is a conjecture, this is that by experiment, but it seems like the Gumbel is quite a good fit, which is also a bit surprising because many times, I've given talks several times and always someone mentioned that, so maybe it's an extreme value phenomenon because the Gumbel distribution is an extreme value distribution, but it's important to say that nothing that we do here is extreme value. So extreme value is about the maximum or minimum of samples, but we look at all the values, not maxima, minima. We look at an entire ensemble of values and somehow the Gumbel distribution shows up. So that's interesting. We don't have any idea why it happens. If anyone has, it's quite welcome. Same thing for the RIPs. Everything is aligning nicely. So that's, yep.
Since the DI is the maxima and minima.
Sorry?
And the death and birth numbers, the maxima and minima.
The death and the birth are maximum.
Yeah, I mean, these are extreme values. And
that could be maybe that's an idea we thought could be sort of indirect explanation, but just as the distribution of values, we don't take minimum values or maximum values. You're right that it could be there's some mesoperimetry or some kind of trying to maximize, minimize, but yeah, we don't have a good explanation for that. It would be really nice if there is a connection to extreme value theory and just saying it's not an obvious one. Okay, so that was the first question. The next question is to, again, experimentally explore more interesting distribution. So to get rid of the IID assumption, one synthetic example is to look at the path of Brownian motion. And then we just sample it at different times. So we have all these points. They are not independent. They are not identically distributed. So we check that, and it works quite nicely here as well. Actually, this is, for some reason, this is the best fit we get among all the distributions. So that's it for Brownian motion. We tried the different other settings. I'll show you a list in a second. We also tried on real data. So this is one really classical sort of example in TDA where they explored the topology of the shape generated by 3x3 patches from images. So you take images, black, white, grayscale, you divide them into 3x3 patches and you look at this 9-dimensional space. Another example that we took is, this is a real audio recording, and then you do the delay embedding. So you have something in high dimension. So you have another point cloud. And for this example as well, coming from completely real data, the distribution still seemed to fit quite nicely. Again, the diagram themselves, the persistence diagram will look vastly different in any of these settings, but somehow when you look at the ratios and you normalize them appropriately, then this thing shows up. One more interesting example is in the world of natural language processing. So especially today, it's quite popular in LLMs. You take, the idea is that you take words or sentences and you encode them with some high dimensional coordinates. And the idea, at least the motivation, is that this encoding will somehow cluster words or sentences according to meaning. So this is just a cartoon example, but the idea is to take words, have some coordinates for each word so that animals will be grouped together, maybe furniture will be grouped together, and so on. And what we did here, we took not word embedding, but sentence embeddings. So this is a 384-dimensional point cloud. We took 3 books. One is the Bible, one is Moby Dick, and one is Ulysses. And again, the same pipeline. You take the RIPS complex here, compute the diagrams, compute this ratio, compute the distributions, and everything fits nicely. So again, for us at least, so already weak universality was a little bit of a miracle, but we sort of took a couple of years to understand where it's coming from. But here we have no idea where this is coming from, especially not when you look at such general type of point clouds that it shows up over and over again. And this is sort of, I think, quite an exhaustive list of settings that we try to check: uniform, non-uniform, non-independent, some real data. We have probably a bit more, different dimensionalities, different homology dimensions. So we put together all these experiments, and sort of our goal is to explore this phenomenon and understand it much better. And this is the main conjecture that we would like to prove, which we call strong universality. So you take this ratio, you take this log-log transformation, and now you look at the empirical measure for these values. And hopefully the statement should be is that no matter anything, no matter what sampling space you use, what probability distribution, what construction you're using or not, or dimension, the limit is always the same limit. And possibly follows this Gumbel distribution or something very, very similar. Okay, so we're nowhere near moving from weak universality to this part. It's a completely, at least this point, looks like a completely different challenge. I should say that it doesn't work all the time, so it's not there's a star here. We would try to look, for example, where it fails. And the example that we did find eventually are examples where there is just maybe too much structure or order in your point cloud or not enough randomness. I don't know exactly how to formulate it, but these are three examples. So an easy one is the perturb grid. You take a grid and you slightly perturb every point. This is a Genibri assembler, which is a repulsive process. So points are sort of uniformly spread out and they don't cluster. And this is another interesting example, which is a simulation that tried to take a point cloud and maximize the number of holes it has in it. So in these three examples, this conjecture failed. And we suspect that it could be related to how ordered the data is or some features like hyperuniformity and things like that, but we don't have any statements here, at least for now. Okay. Yeah, so this is the results we have. And for the last part, I just want to mention a couple of applications we sort of thought of as a first stage, but we're hopeful that there are going to be more. The idea, at least from the perspective of topological data analysis, is now that if we remind you that we have signal and noise in those diagrams, but now we know that the noise have only one distribution, and we sort of know what it is, potentially this Gumbel distribution. So if we want to build statistical tests, we can just assume that everything is Gumbel and use that. And that's sort of one idea, so hypothesis testing. So you have a given point cloud, you look at the diagram, and the question here to formulate is you pick one of the points and you want to ask, is this point part of the signal or part of the noise? Is it important enough? Is it something interesting, or it's just an artifact of your sample? And you could phrase it as a hypothesis testing question, where the null hypothesis would be to say it's noise, and now you need to prove that it's not. And the point is that we know, or at least if you believe the conjecture I put before, is that the noise has just one distribution we have to look at. So we know exactly how it's distributed. It's the same no matter how the data was sampled. So we can compute p-values to measure how likely this point is to appear if it was coming from the noise, and then decide whether we reject the null hypothesis or not. And the advantage here is that we need very, very, very little knowledge about how the data was sampled. We don't need to know the distribution of the data, not even presumably the dimensionality of the data, or hardly anything else. We didn't need to know that universality holds, but then there are sort of there are ways to verify it before you use the method. And here is an example. So here we have two point clouds, which are quite similar. One is coming from a figure 8, so there should be two holes in here. The other one is almost a figure 8, but we sort of removed this gap here. So topologically, you want to say that here you observe two cycles, and here you should observe only one. So the black points here correspond to the black points here, and the white correspond to the whites, and you see the diagrams. So in both diagrams, you have two features that sort of, if you just look at the distance to the diagonal, here you have two features, and here you have two cycles. So if you're not doing any statistics, you would say in both examples that you have two significant cycles. But what we can do now is to use the universal distribution to quantify for each of these points how significant it is. And then there is a line we can draw here to say, okay, everything below that line is significant with 0.05 significance, for example. Okay, and you see that for the black point, indeed, two features stand out sufficiently significant, whereas for the white ones, only one of them we can declare it as statistically significant. The other one, we cannot reject the null hypothesis, which sort of is a nice way to distinguish between these two point clouds. So that's one potential use for this kind of framework. And another application we sort of explored recently is for clustering. And here we we build a slightly non-standard filtration of graphs. So what we do is, we call it the K-cluster sequence. So we connect points in the graph, we place an edge whenever 2 points are close enough. But we ignore all the vertices and all the edges in the graph as long as they don't belong to a cluster of size K. There are several reasons why we do that. And then we increase the value of R. So we add more and more edges this way. And we want to track the evolution of the components, which in homology are the zero-dimensional cycle. So the sequence is like that. Everything is gray, is not being considered at the moment. Whenever you have points, in this case, that belong to a cluster of size 3 or more, they will show up with the edges. Everything else is ignored. So there's an edge here, but we don't see it. We ignore it. And we keep doing that. So more clusters eventually will show up. So now we have 4 clusters showing up. Again, these edges are ignored. And then if we keep doing that, at some point, we're going to see the 2 main clusters. So it sort of captured the structure here, which looks like 2 clusters. And another interesting or nice feature is that the outliers, the things that are sort of far away, we will never see them. They will only join once everything is already connected, and they will just join one of the clusters. So the outliers here will not confuse us as being another cluster. So this is the kind of filtration we're using. K is a parameter you need to choose, saying how big of clusters you want to track. Okay. Okay, so this is the picture, and now you have a filtration, you have a sequence of these graphs, you can compute persistent diagrams for the component, for the clusters. And then what you get is that every cluster has its own birth time whenever a group of vertices form a large enough cluster, and a death time, which represent when 2 clusters sort of merge together, so one of them disappeared. And for this data set, you see 5 different clusters that appeared, and in the picture, they correspond to this 1, 2, 3, 4, 5 cluster. Again, these 2 are ignored, they're not part of the filtration. So there are 5 clusters that appear at different times, they merge at different times, and this is the diagram that we get. So this kind of procedure gives you sort of an interesting rich information about clusters that you see in your point cloud. And one of its nice features is that it's robust to outliers, because the outliers will never appear, they will just join one of the existing clusters. But in our context, the most interesting part is that now we have another filtration, we can do the same trick, we can compute depth birth, we can compute the distribution, and still everything holds very, very nicely the same way as before. So the strong universality holds also in this context, which is quite different in taste than what we've done before with homology and cycles and so on, even though it's still to some extent homology. And this can be useful for designing what are your clusters. So here are 2 examples. You have a mixture of 3 and 4 Gaussians. You do this filtration, I think here it's with K equal 20, so we only track clusters of size 20 and above. We have this diagram over here. It seems like there are 3 features that are outstanding, which correspond with what should be. Here there seem to be 1, 2, 3, 4 features also corresponding, but again, this is the picture. The question is how to do statistics on that picture. And the idea would be, again, we have the universal distribution describing the noise. So for each feature here, for each cluster, we can quantify whether it's statistically significant, namely it's a cluster, or it's part of the noise. And yeah, so we run it against a few other clustering algorithms with this test case that appear in Python. And so there are k-means, spectral clustering, and other methods. The 2 last columns are this K cluster filtration with K equal 5 and 10, and it seems like it's capturing the correct structure. In most of the examples, this is the only place where something is missed. One cluster is not statistically significant, but again, the idea would be to generate this filtration, look at the persistent diagrams, use the universal distribution to decide what is significant and what not, and then track it back to the clusters and paint them, color them. So this is another, again, this is just a toy example, but another potential application for this theory. And I'll finish with that. So what I show you today, again, some new results in stochastic topology, which are a little bit unexpected, which tells you that if you generate random point cloud, you look at the diagram in a certain way via those death to birth ratio, then it always ends up with the same distribution. We have a theorem for what we call weak universality, where you have to assume the points are independent. The limit there depends on several things, like the dimension. And we have a conjecture for strong universality, which basically applies to most of the data set we tried, even real data. The limit is always the same limit. It looks like the Gumbel distribution. And there are several ideas for applications. I mentioned the hypothesis testing and clustering. With the example I showed you before, maybe there is a way to measure how your point cloud is disordered via those distributions, dimensionality estimations, and other things. So I'll finish with that. Thank you.
Great, thanks, Omer. I think we've got time for maybe one or two quick questions before lunch. So should we start over here?
Okay, thank you very much. Very interesting. I'm curious about the slot log transformation. Is there any motivation behind this slot log? Because the resulting distribution is
there is. It's going to be a very stupid motivation. When you look at that to birth ratio, it's always 1 and above. Okay, so when you try to fit there are not so many known distributions start at 1 to infinity. So we took 1 log, so now you're 0 to infinity, but still it's not so many. We wanted something that goes from minus infinity to infinity, for example, to see if it's like the normal distribution, so we just took 2 logs. That's the stupid reason, but again, we tried fitting everything with 1 log, with no log, and that was the best fit, so we stuck with that, and then, yeah.
Does it A and B parameter methods?
So the A, yeah, I didn't put it in this talk. The A is a weird thing. It's what we found is that it should be, if you take check complex, it's 1. If you take Rips complex, it's 1/2. Why, I don't know, but it's quite consistent. The B is just the average. So it's just centering the point. So it just, you compute the average, you move everything, but it's that's the only thing.
I would suggest that you try to prove your conjecture first for Brownian motion, because somehow it depends on some kind of conformal invariance, and there's a lot of machinery there, work of Wendelin and Smirnov also, that related to conformal field theory, and there might be tools available there.
I agree. It also seems that the simulations are quite work the nicest way with the Brownian motion. I also think it could be related maybe to the fractal nature of the Brownian motion, but I agree. It's for non-IID, it's like a really nice
yeah, I think that's
starting point.
the basic case where you could check it.
Yeah, thank you.